Now that we know a little bit about electron configurations, I want to start thinking about valence electrons, which are the electrons that are associated with an atom, that are the ones that are most likely to react with other atoms, or most likely to form bonds, or be taken away, or shared in some way with other atoms. And we've already kind of talked a little bit about this as we talked about the trends through the periodic table, but now we'll do it a little bit more formally, and we'll use what we call Lewis dot structures to visualize these. So, as I said, these tend to be the highest energy, and furthest out. And you might be saying, well, aren't the highest energy the furthest out, or aren't the furthest out the highest energy electrons? Well, that is true if we're talking about the S block, if we're talking about the S block right over here, or if we're talking about the P block, right over here. But that is not true. That is not necessarily true for the transition metals, for the non-main block elements. And so that's why I'm not using an absolute. I'm saying it tends to be the highest energy furthest out electrons. So let's think this through a little bit, and let's try to draw some Lewis dot structure. So we could start with the simplest of elements. We could start with hydrogen. Hydrogen has one electron. Its electron configuration is 1s1. That one electron is its one valence electron. That's the electron that hydrogen will use when it reacts. It could be swiped away from hydrogen, where hydrogen will just become a positive ion, or maybe it'll share it with another one. It can share this electron with another atom, and that atom will share an electron with it, and then hydrogen maybe could pretend to have a more stable configuration like helium. But that's its one valence electron. We would do that just as a dot around the hydrogen. Now, what about other group 1 elements? Let's say sodium. So sodium, what's its electron configuration? Well, I'll use a shorthand where we could say, well, its base configuration is the same as neon. It has the base configuration of neon. So neon would, it's 1s2, 2s2, 2p6. That's what this represents. And then to get to sodium, you would then have 3s1. 3s1. So how many valence electrons does sodium have? Well, its highest energy furthest out electron, I say the electron that's in a non-stable shell, that's in a shell that hasn't been stabilized, it hasn't gotten to its fully stable state. There's only one electron in that situation, right over here, the 3s1 electron. And so sodium as well, you could depict like that. It only has one valence electron. That's the electron that could be swiped away from it, or that somehow could be involved in a covalent bond somehow. Now let's do things with more valence electrons than hydrogen or sodium. But the important thing to realize, actually for the example of hydrogen and sodium, is that all of these group 1 elements are going to have one valence electron. They're going to have one electron that they tend to use when they are either getting lost to form an ion, or that they might be able to use to form a covalent bond. Now, let's think about helium. And helium's an interesting character because all of the rest of the noble gases have 8 valence electrons, which makes them very stable. But helium only has 2 valence electrons. But the reason why it's included here is because helium is also very stable, because for that first shell, you only need 2 electrons to feel full, to feel stable. And so helium has two valence electrons. Its electron configuration is 1s2. And once again, the reason why it's out here with the noble gases is because it's very stable and very inert like the noble gases. That's why we now use helium for balloons instead of hydrogen. It's not going to blow up like the Hindenburg. But you might say, well, if it has 2 valence electrons, maybe it should be in group 2, because wouldn't all of the group 2 elements have 2 valence electrons? And that actually would be a very reasonable argument, and we've seen that already. One could make a very reasonable argument to put helium in group 2 for that reason. All of the elements in group 2 are going to have 2 valence electrons. Now let's jump to one of the most interesting and versatile elements in the periodic table, the one that really forms the basis of life as we know it, and that's carbon. So I encourage you to pause this video, and based on what we've just talked about, think about how many valence electrons carbon has and what its Lewis dot structure could look like. Well, carbon's electron configuration is going to be the same as helium plus is going to be the same as helium, plus you're going to have 2s2, and then 2p2, 2p2. So how many electrons does it have in its outermost shell that has not been completed yet? Well, it has these four, 2 plus 2. So we could depict them as 1, 2, 3, 4 valence electrons. Now, why is this interesting? Well, we can now think about, especially if we see carbon's valence electrons and we see hydrogens in this Lewis dot structure, we can begin to predict what types of molecules carbon and hydrogen could form together. So, for example, carbon would like to get to 8. It would like to pretend like it has 8 electrons, so it feels more stable like the noble gas neon. And hydrogen would like to at least feel like it has 2 electrons in its outermost shell, so it can feel more stable like helium. And so if these are carbon atoms, and if these are hydrogen atoms, I'll do the hydrogen orange. Hydrogen in, actually, let me do it this way. Hydrogen, 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 and actually, let me do it the way I was doing it at first. So you could imagine something like this, where carbon could bond, just based on what we've kind of learned about valence electrons and Lewis dot structures. You could say, well, I would predict that maybe a molecule like this could form, where a carbon shares its 4 valence electrons with 4 different hydrogens, and in exchange it shares an electron from each of those 4 hydrogens, and so the carbon can feel like it has 8 valence electrons, and each of the hydrogens can feel like it has 2 valence electrons. And if you did this, if you said, well, there should be some molecule out there in nature that seems pretty stable like this, you would be absolutely correct. This is methane. And the way that this would be depicted with the Lewis dot structure is this, right? What I did over here is less conventional notation. Each of these electron pairs, so that electron pair would be represented as a covalent bond. This would be represented as a covalent bond. That would be represented as a covalent bond. That would be represented as a covalent bond. Each of these bonds are the sharing of essentially 2 electrons. The two electrons. So carbon can feel like it has 2, 4, 6, 8 electrons, even though it's sharing them. And each of the hydrogens can feel like they have 2 electrons, which gets it into a more stable state. And any of the elements in carbon's group, they are all going to have 4 valence electrons. So, for example, tin. Even though neutral tin is going to have 50 electrons, the valence electrons, the ones that are going to react, are going to be the 1, 2, 3, 4 in its outer shell. 1, 2, 3, 4. And so you might predict, well, maybe it could form bonds not too different, or it might react in a similar way in some ways to, say, something like carbon. Or maybe silicon could react something similar to, say, carbon. And people even think there could be life forms on other planets that aren't based on carbon, but actually are based on silicon, because silicon would have similar types of bonds, and it can form similar types of structures to carbon for this exact reason. Now, what about, I kind of said that you have your transition metals, your D block right over here, and actually your F blocks are going to be thrown in here as well. And these are special cases, and these get a little bit more involved, because as we already learned, that once you're in the 4th period, so let's say we want to do the electron configuration. Let's say we want to do the electron configuration of, say, iron. Iron's electron configuration, we could start with argon as a base. We can start with argon as a base, and then we're going to go 4s2. We're going to go 4s2, and then we're now in the D block, but we're not going to fill the 4th D, the 4D suborbital. We're now going to back up and backfill into the 3D suborbital. So it's 1, 2, 3, 4, 5, 6. So it's 3D6. So this is where this gets a little bit more ambiguous. What are the highest energy electrons? Well, those are these D electrons right over here. What are the furthest out? Well, they're the ones in the 4th subshell, these 4s2. And so that's why iron's reactivity is a little bit, at least based on just this superficial electron configuration, it's a little bit harder to predict. Iron is known to lose 1 electron, known to lose 2 electrons, known to lose 3 electrons, and so those could be some combination of these highest energy electrons, both the ones that are furthest out and the ones that are highest energy. So iron becomes, and as all of the transition elements, figuring out the valence electrons, the electrons that are most likely to react, becomes a little bit harder to predict. Some people, some even textbooks, will say, oh, all the transition metals have 2 valence electrons because they all get to 4s2 and then they're backfilling. And so they would say, okay, these are the 2 valence electrons for all of these transition metals. Well, that doesn't hold up for all of them because you even have special cases like copper and chromium that only go 4s1 and then start filling 3d, depending on the circumstances. Sometimes it does it otherwise. But they're not necessarily. But even for the other transition elements, like say iron, it's not necessarily the case that these are the only 2 electrons that are going to react. You might have some of your d electrons, your 3d electrons, which are high energy, might also be involved in a reaction, might be taken away, or might form a bond somehow.